everyone, welcome to IIT-JAM in Chemistry tutorial number 6 and lecture number 2 of Atomic and Molecular Structure. Today's subtopics which are going to be discussed are the Bohr's theory, the principal quantum number, radius of orbit, velocity of an electron, Bohr's orbit and Bohr's radius. Let's start from the Bohr's theory. First of all, electrons can move around the nucleus only in certain stationary orbits and do not radiate energy. The angular momentum of each electron is an integral multiple of h by twice pi, that is mbr equals to nh by twice pi, where n is a positive integer. The other symbols have their own significances. Let me explain. M is the mass of the electron, v is the velocity of the electron, and r is the radius of the orbit along which the electron is moving around. So mbr is the angular momentum, and this is the integral multiple of the value h by twice pi, where h is the Planck's constant. So n is a positive integer. It should have the value either 1, or 2 or 3 or etc. So mvr must be equal to h by twice pi or twice h by twice pi or thrice h by twice pi, etc. Okay, and number 2, for electronic transitions from one orbit to another, the Planck's equation, which is E equals to h nu, this is obeyed. If an electron jumps from the second level to the first level, then the energy radiated. What is the energy radiated? This is delta E, and it is equals to nothing but E2 minus E1, which is equal to h nu. Nu is the frequency of the radiation which is radiated due to jumping from the higher level to the lower level. Now, relationship between orbit radius and the principal quantum number n. Okay. So here we have to equate the centrifugal force with the electrostatic attraction. So the centrifugal force of the electron due to its circular motion around the nucleus is balanced by the electrostatic attraction between the nucleus and the electron. That means the equation must be here mv square by r equals to z square by 4 pi epsilon 0 r square. Here m is the mass of the electron, v is the velocity of the electron, r is the radius. Z is the atomic number, E is the charge of the electron, epsilon 0 is the permittivity of vacuum, and R again the radius. Okay, so here all these values are given, and the value of epsilon 0 is 8.854 into 10 to the power minus 12 coulomb square per Newton per meter square. Now, let us rearrange this equation. Just take the r, this part denominator, to the right hand side, and it gets the form mv square equals to z square by 4 pi epsilon 0 r, and this is equation number 1. And from Bohr's theory, the angular momentum, we have the value mvr equals to nh by twice pi. So now rearranging mvr equals to nh by twice pi, we get v equals to nh by twice pi mr, and we have to put this value in the equation number 1, where we have already obtained. And in equation number 1, in place of v square, we are putting nh by twice pi mr whole square. Okay, and the right hand side is same, z square by 4 pi epsilon 0 r. And as a result, after having rearranged this form, we have got the expression of r. So this is the relationship between the principal quantum number and the radius of the orbit. Okay, so r equals to n square h square epsilon 0 divided by pi mz e square. This is equation number 2, and let's block this. Okay, now here z is the atomic number, this is a constant, this is a constant, this is a constant, constant, whereas these two are variables. N is the principal quantum number. This integral multiple becomes the principal quantum number. For orbit number 1, this is 1, orbit number 2, this is 2, etc. So h is also the constant, but z is not the constant. Z is varies from element to element. For hydrogen this is 1, for helium this is 2. So here the variable terms are n and z only, and other terms h, epsilon 0, pi, m and e are constants. So from here you can make a variable relationship, proportionality relationship, which is r varies as n square by z. Okay, this will be a very useful equation in order to calculate with the reference of the radius of one orbit. With the help of that, you can calculate the radius of other orbit of any other atom. Now question number 6 of this chapter. 5 questions have been already discussed in the previous lecture number 1, and you must get the link, video link, in the description box if you have missed that video. Okay, so let's discuss question number 6 here. This is, if a normal hydrogen molecule is 2.2 angstrom in diameter when both the electrons are in the most stable Bohr orbit, what should be the size of a hypothetical molecule in which the electrons were each in the third Bohr orbit? Did you understand this question? So the electrons are occupying the first Bohr orbit. So from that context, it should have a certain diameter. It is 2.2 angstrom here. But if hypothetically they are occupying the third Bohr orbit, then what should be the diameter? Okay, that means you have to calculate the radius actually. So this is the picture. Okay, so electrons are occupying the first Bohr orbit. This is the first Bohr orbit of the first atom. This is the first Bohr orbit of the second atom, and this is the overall diameter. Okay, 2.2 angstrom. So this 2.2 angstrom diameter means this one radius number 2, radius number 3, radius number 4. So you have to cover 4 radius along this line. So this is actually 4r. Okay, so for n equals to 1, that means for when the electrons are occupying the first Bohr orbit, this 4r is nothing but equal to 2.2 angstrom. So here the radius r is 0.55 angstrom, just 2.2 divided by 4. And just I have said that this proportionality relationship, r varies as n square by z, would be very much useful in order to calculate. So we have to utilize this. So we know that r varies as n square by z. Okay, and for hydrogen, z equals to 1. Okay, this line not necessary right now. Z equals to 1, and if z equals to 1, then r by n square is constant, isn't it? Because here for hydrogen, the first Bohr orbit z equal to 1, for the third Bohr orbit also z equal to 1, because the atom is not changing. Okay, so z becomes constant here in this particular case. So r by n square is constant, means r1 by r2 equals to n1 square by n2 square. Now we have the values of r1 and n1 and n2, isn't it? And what are the values? r1 is 0.55 angstrom, n1 is 1 because this is the first Bohr orbit, n2 should be 3 because this is the hypothetical third Bohr orbit. And just putting these 3 values, you can easily get the value of the r2. Okay, and this is 19.8 angstrom. And if r2 is 19.8 angstrom, then what is the diameter of the hypothetical atom? The size of the molecule, that is size of the molecule, it should be multiplied by 4, isn't it? If this one is now 19.8, this to this, from center to this circumference, then it should be 4 into this radius. So this value is 39.2 angstrom. Okay, let's move on to the next topic, relationship between linear velocity v and principal quantum number n. And here again recalling equation number 1, by equating the centrifugal force of the electron due to its circular motion around the nucleus and the electrostatic attraction between the nucleus and the electron, we already have equation number 1. Now according to the Bohr's theory, mvr equals to nh by twice pi, and here instead of v we are taking the value of r, and we have to insert this value of r here in equation number 1. Okay, so the value of r is nh by twice pi mv, and putting the value of r in equation number 1, we have mv square in the left hand side as usual, and in the right hand side z square by 4 pi epsilon 0. Instead of r we are inserting the value nh by twice pi mv, which is obtained from the Bohr's theory. Okay, and rearranging this equation, we get equation number 3 here, and which gives the value of v as a function of z and n, because these are all constant, e, epsilon 0 and h. So from here we can get a proportionality relationship also, which is v versus z by n. This is also very much useful. Okay, so for a certain atom where z is a constant, if the atom is constant, that means if it's only from hydrogen to hydrogen, not from hydrogen to helium, then in that case it is v varies 1 by n. That is, linear velocity is maximum at the first Bohr orbit. That is also an important question. Where is the linear velocity maximum? So the answer is in the first Bohr orbit. Okay. Now move on to the second question of today's chapter, today's lecture, and the seventh question of this chapter. It is, if an electron travels with a linear velocity of 1 by 100th speed of light in the first Bohr orbit of hydrogen atom, what is its velocity with respect to light in the fifth Bohr orbit? So it is both cases the same atom hydrogen, and for that z equals to 1 in both cases. So instead of v varies as z by n, we have to utilize the relationship v varies as 1 by n. That means v1 by v2 equals to n2 by n1, isn't it? So this is the relationship, and you got to find out the value of v2. So it is nothing but v1 n1 by n2, and put the value here, the value of v1, okay, the speed of light, and here it is divided by 100 because it is 1 by 100th speed of the speed of light, and here n1 is 1 and n2 is 5, so it is c into 1 by 500. Okay, therefore it should be 1 by 500th speed of light. Okay, so the linear velocity in the fifth Bohr orbit is just 5 times less than the first one. So that's all about this question, and let's move on to the next subtopic, which is concept of Bohr orbit and Bohr radius. Due to its limitations, the Bohr theory is applicable only to the hydrogen atom. This is very important. This is not possible to apply this theory to other atoms, okay, and the hydrogen molecule also, and hence the orbits in the hydrogen atom are known as the Bohr orbits. Okay, let's calculate the radius of the first Bohr orbit, and the first Bohr orbit is denoted as a0. Okay, now we have to use the equation number 2 here in this context, where the expression of r we have n square h square by epsilon 0 over pi m z e square. So for hydrogen atom, for first Bohr orbit, n should be 1 and z should be 1 also, and h, you have to put the SI unit value 6.626 into 10 to the power minus 34 joule second, and epsilon 0, permittivity of vacuum, 8.854 into 10 to the minus 12 coulomb per Newton square per meter, and pi has its own value, 3 point something, m is 9.11 into 10 to the power minus 31 kilogram, and e, charge of an electron, 1.602 into 10 to the minus 19 coulomb. So we have to put this corresponding values. Okay, and finally we get this in the SI unit. Okay, the value is 5.292 into 10 to the power minus 11 meter. That is, it is 0.5292 into 10 to the minus 10 meter. That means 1 angstrom equals to 10 to the minus 10 meter. So if you remove this, or if you eliminate this 10 to the minus 10, then this meter would be converted into angstrom. So the radius of the first Bohr orbit is 0.5292 angstrom. Sometimes it is also approximated as 0.53. Okay, so this is the radius of the first Bohr orbit. So you have to memorize this value because this will be utilized in some cases also in future. This is known as the Bohr's radius. Okay, now the next question. Calculate the radius of the nth Bohr orbit. If the first Bohr orbit is 0.5292, then what should be the value of nth Bohr orbit? Very important question. So for hydrogen, z equals to 1, and the relationship from the proportionality relationship we can write easily, r1 by r2 equals to n1 square by n2 square. And for n1 we have r1, that is actually a0, which is nothing but equal to 0.5292 angstrom. So for n2, which is n, any Bohr orbit, okay, and r2 is r, any radius, so that r should be, just put these values, 0.5292, here n square, here 1 square. So this is nothing but 0.95292 n square angstrom. So this is the answer. So that's all for today's lecture. Thank you.